So, our next keynote speaker is Oliver Charles. Ollie works at CircuitHub, and he's a senior Haskell developer, also works with Elm, and he's also interested in graphics and game development in Haskell. And he's probably most known in the community for his blog post series 24 Days of Hackage, which is, has come in 2 installments, I think, yet, and 24 Days of Haskell extensions. Today, he's going to talk about fast downward and solving planning problems in Haskell. Thank you.
Thank you. All right, morning everyone. So today I want to talk to you about a project called Fast Downward. We're going to see that Fast Downward is actually a kind of umbrella term with 2 separate but related concepts. So on the one hand, we have Fast Downward, which is a standalone C++ executable, nothing to do with Haskell, and this is an executable for solving what are called planning problems. We'll see what a planning problem is in just a little bit. On the other hand, Fast Downward is a Haskell project. This is something that I'm responsible for, so there's a library on Hackage called Fast Downward, freely available open source software, and it's an embedded domain-specific language for this Fast Downward executable. And in this talk, I want to see how we can bring these 2 things together to solve what I call declarative planning problems directly in Haskell, so we never have to leave Haskell at all. But what is a planning problem? I think the best way I can explain what a planning problem is and to provide some motivation is to explain it in the context of CircuitHub, which is where I did all of this work on Fast Downward. So CircuitHub, I think the best way to understand this is we do circuit board manufacturing as a service. So that also says what we don't do. We don't do chip design and we don't do circuit board design. We really work with electronics engineers who have electronics projects themselves. They have some problem in the real world that requires some custom hardware, so they do some circuit board design and then they need to actually have a physical circuit board. So we can produce that circuit board directly to their designs. So electronics engineers work in CAD software, so here we've got a couple, KiCad, Altium and Eagle are all industry standard pieces of software for designing circuit boards. CircuitHub natively supports all of these formats, so you can just upload your raw design files directly to CircuitHub. There's no custom export process, no custom editor required. Give us exactly what you have and we'll take it from there. So we parse these design files into our own internal schema, present this through our website so you can actually see if the import process went successfully or not. You can make any last minute adjustments there, but once you're happy, we give you basically 2 order parameters, which is how many circuit boards you want and how long you're willing to wait for those circuit boards to be produced. And with all of that information, we can generate a dynamic quote on the fly so you know exactly how much your circuit board is going to cost. So this is what it looks like. This is one of the public projects on CircuitHub. You can see we've got a kind of ability to kind of share a bit of information about a project. Down here is the bill of materials, so all of the parts that are involved in the circuit board. And the kind of interesting thing is down the bottom, we've got these 2 parameters, so how many you want and how long you're willing to wait. That updates the price kind of live on the fly, and then you can hit order and just sit back, and in that amount of time, you should receive some circuit boards from CircuitHub if all goes well. So in order to actually achieve this operation, like CircuitHub generally processes around 50 to 100 unique orders per month, and an order can be anywhere between about 50 circuit boards up to 1,000 circuit boards. So there's a lot of volume going on. So in order to produce all of this, we actually have our own factory based in Massachusetts. This is a kind of standard circuit board manufacturing factory. So we have pick and place machines, which allow you to do surface mount soldering, and they paste parts on circuit boards. We have some solder paste printing machines, which are essentially high precision jet printers that can very accurately place solder onto circuit boards. We have some high resolution imaging machines, so we can inspect the quality of the build at any point in time. But I think most interestingly is that we're a software first company, even when it comes to this idea of running a factory. So what do I mean by software first? So all of these machines I've talked about, actually we have little Haskell libraries that sit in front of these machines. So I can interact with any of these machines programmatically and kind of script them directly using Haskell, and I just treat them as a library. But even this whole concept of a factory is itself a piece of software that I can interact with as a programmer. To understand the motivation there, I think it's helpful to kind of look at the way you would traditionally run a factory. So I think much like you have an imperative programming model, there is also a kind of imperative model to traditionally running factories. So engineers who work in a factory have kind of high-level objectives that they're trying to achieve. They might be trying to build all circuit boards for a customer's order, or maybe a single board for a customer's order. But they have to interact with the factory in a kind of low-level fashion. They have to tell the factory what it is the factory has to do in order for the engineer to achieve this goal. So to give you one example, something that happens all the time in CircuitHub is we receive a brand new set of circuit boards for a customer's order. So we don't print PCBs ourselves at the moment. We have a third-party supplier do that. And the first thing that I'm interested in is taking high-resolution images of these circuit boards to understand the quality of them before I begin any more of the production process. So this seems like a fairly easy task to do. I just take a circuit board, I go over to the imaging machine, and I place the circuit board in the imaging machine. The problem is I don't know the state of the imaging machine when I actually begin this operation, so there may already be a circuit board in the imaging machine, in which case I have to take that circuit board out of the imaging machine, I have to store the circuit board that I was previously holding. But even the process of taking a circuit board out of a machine is a non-trivial task. If that circuit board has solder paste on it and the solder paste isn't set and there are parts in the solder paste, if I move that circuit board too quickly, I'm going to end up damaging the quality of the build so far. So I have to be very careful when I take the circuit board out, and there might be moisture-sensitive parts on this circuit board, so I might have to place it in a particular storage location. So this one kind of task that I was trying to do of placing a circuit board in a machine has spawned out multiple new tasks along the way, none of which were particularly interesting things for me to do, but it also required a lot of knowledge of the internal constraints of how we do things at CircuitHub. So that idea of placing certain circuit boards in certain locations isn't essential. I could put stuff anywhere I wanted, but it will invalidate the quality of the build. So I want to maintain these constraints all the way along the way. So much like we have a kind of dual to imperative programming, which is declarative programming, I think there's a similar model of running a factory declaratively. So I want to be able to talk to the factory as some kind of abstract entity and just tell it what I want to have been achieved. And then I can let the factory do the hard work of working out how to actually achieve this goal. So this is going to require a little piece of software to kind of act as the brain of the factory. But I, as an engineer, then get to say to the factory things such as circuit board 572 must have high-resolution images. And from that point on, the factory can work out that it needs to satisfy certain constraints, such as clearing the machine and making sure to put things in the correct location. So software coordinates this work as efficiently as possible. And this, it turns out, is actually an instance of a planning problem. So Wikipedia, the source of all unquestionable knowledge, has this to say about planning problems. So given a description of the possible initial states of the world, a description of the desired goals, and a description of a set of possible actions, the planning problem is to synthesize a plan that is guaranteed to generate a state which contains the desired goals. So that's a little bit wordy. I like to kind of think of it as you have some kind of deterministic system that you're working with. You can model this in code, so you can capture the individual states of the system at any point in time. It's deterministic, so you know how this system will transition over time. And we're interested in moving from a known initial state to some other state in the future that satisfies certain predicates of things that we're interested in. So to look at an example planning problem now, I'm going to move away from all the stuff we've talked about at CircuitHub and just look at some kind of simpler examples. So here we have a problem where I've got some kind of agent that can move around a two-dimensional space. It can move in unit increments along both of the axes. And we're interested in the problem, how does it move from the point 3,3 to the location 5,6? So this we can encode as a planning problem quite easily. We need to model this as this idea of a deterministic state machine, essentially. So we have our states are simply pairs of x and y coordinates. X and y coordinates are just integers, and they're between 0 and 6. The actions in this system are, we can either move the agent forwards, backwards, left, or right. It just has 4 movements. We have an initial state at 3,3 and a goal state at 5,6. So this describes the problem, but of course a planning problem doesn't tell me anything about how to actually solve this and come up with a solution. So there are multiple different ways we can solve planning problems, but to me, one of the most intuitive ways of doing it is this slight mouthful of forward chaining state space search. But the idea is we try and re-encode that problem as some kind of graph. So a graph has nodes and edges. The nodes in this graph are going to be the possible states we could be in at any point in time. And the edges in the graph are state transitions, how we can move from one state to another. So the planning problem now is actually just translated into a graph search problem. We need to find paths from the initial state to the goal state. And that's a pretty well-known problem to solve. There are multiple ways to do that. One of these is to use breadth-first search. So we can start at our initial node in the graph, and then we just kind of repeatedly search out from that point. So we find all immediately reachable states from our initial state. We check if any of these are the goal state, in which case we're kind of trivially done. And if not, we need to repeat that process for each of the newly discovered states that we could reach. So let's have a look at breadth-first search applied to moving this agent around a two-dimensional search space. So we can lay out the search space quite intuitively. The states all corresponded to XY coordinates. So every single one of these kind of squares corresponds to a location the agent could be in at some point in time. In orange, we have our kind of starting location at point 3, 3, and we're interested in moving up to this green square at 5, 6. And all of the edges here correspond to the movements we could take in a single action. So breadth-first search begins by just expanding that node and finding all immediately reachable states from there. And we can see none of these are the green square, so we're going to need to repeat the process. So for each of these newly discovered states that we've found, we can just expand those, and we kind of radiate the search out from our initial point. We do this again, we do this again, and eventually now, if we expand either of these top two states in the top right, we're going to reach our goal, which allows us to recover a path from that goal back to the root. So this is obviously quite a hand-wavy explanation. There's a little bit of bookkeeping that has to go on along the way in order to recover this path once you've reached your goal, but it's a pretty well-studied algorithm, and I'm not really going to focus too much on the details there. But let's look at just the kind of properties of breadth-first search. So one very nice property is that breadth-first search is a complete search algorithm, which means if there is a path from your initial state to a goal state, breadth-first search is guaranteed to find it. It's also an optimal search algorithm in the sense that the search path that you get back contains the minimal number of edges you need to take. So it's the shortest path algorithm as well. So those are very nice properties because it means we won't have redundant work and we're always guaranteed to find solutions if they exist. And perhaps most interestingly is it requires no domain-specific knowledge. So it's a very general-purpose algorithm. So when we were expanding the search grid before, we didn't actually say that we were exploring a two-dimensional search space. That just fell out naturally from the shape of the graph as we encoded it. The downside is, of course, it's extremely inefficient. Because there is no domain-specific knowledge, there's no way to guide the search in any particular direction. It just simply has to consider everything equally. And we get a notion of efficiency if we look at exactly how many states we actually had to explore to come up with the solution. So in this 6x6 grid, there are 36 possible states, and we've explored 32 of them. So there are only 4 states that we didn't consider when we came up with the solution. For a search space as small as this, that's really not a problem. You can get through that trivially, but search spaces are often in millions and billions of potential nodes. The moment you have kind of states interacting, you get this combinatorial explosion of all the states you could possibly be in. So just naively enumerating a breadth-first search very rarely actually comes up with solutions in any meaningful amount of time. So what we need to do is we need to extend breadth-first search with a bit more information. We need to improve on this by being able to guide that search. This is a well-studied problem. So the Astar Search algorithm has been around since about 1968. And it improves on breadth-first search by just trying to inform that search process. And the main addition of Astar Search is to use what are called heuristic functions, which approximately answer the question, am I getting any closer to the goal that I'm looking for? So in terms of the algorithm, it's roughly the same, but now we need to maintain a priority-ordered queue based on these heuristic scores. But otherwise, it's a similar kind of expansion process from the initial starting point. So applying this to this two-dimensional search problem, we begin by simply expanding the node as we did before, but now we need to score all of these nodes with a heuristic function. And at this point, we have a choice to make, because Astar doesn't prescribe any particular heuristic function. It's up to us to choose one that's suitable for the space that we're searching. So a nice heuristic function for exploring a two-dimensional search plane is to just take the straight line distance between any 2 nodes. So this is not a legal movement in the system. The robot isn't able to move in a straight line directly to its goal, but it does a good job of approximating the movement that we can actually take. So if we score all of these are the square distances. You can see some of these are clearly closer to the goal, so they've got a lower score, and those are the ones that we're going to focus our search on. So the lowest score we have is 8, so we're going to expand that node. That gives us 3 new nodes, because we're not going to consider backtracking, and we do the same process. We score those with the straight line distance. We then consider the lowest possible scoring node that we've seen overall, so 5 is now lower than anything we've ever seen. I'm just going to break the tie arbitrarily by going forwards in this case. Repeat the process of taking the distance, choosing the lowest scoring node, which is now 2, so we're going to focus there. We get 2 new nodes. We're not going to consider this node down here because we've already got a path there, which is going to be shorter than kind of doing this roundabout route to it. We score these with the heuristic function. I'm going to break the tie by just going to the right now, expanding that, and we now see that we've expanded towards our goal state, so we can recover the path again. So again, slightly hand-wavy. There's a little bit of bookkeeping that has to happen along the way to actually get a path out of this, but that's, again, just kind of programming. It's not too hard at that point. So Astar Search, also a complete search algorithm, also an optimal search algorithm, but a considerably more efficient algorithm than breadth-first search. So again, that notion of efficiency, we can just look at the amount of states that we actually had to explore, and we haven't even considered going down to all the way to the left or all the way to the right now. The downside is that that kind of blessing of efficiency is also a curse, because it's very hard to come up with general-purpose heuristic functions. So heuristic functions should give us that approximate distance metric from any state to the goal state, and it's generally domain-specific. So heuristic functions sometimes exist in particular domains, such as pathfinding, where it's very easy to come up with these kind of straight-line distances, and we can augment those with a little bit more information. But I'm interested as a Haskell programmer as kind of general solutions to problems. So what's a general heuristic function between arbitrary states without being domain-specific? Like, what is the heuristic function that compares CircuitHub factory states? If I have circuit boards in one location and another state where the circuit boards are in a different location, is that closer to a goal? And I got quite stuck on this problem for a while. But the good news is, I don't actually have to answer this problem. As I searched around for these notions of more powerful heuristic functions, I came across this project called Fast Downward. I found the somewhat poorly hidden Fast Downward homepage. And it turns out that Fast Downward originally came out of a research paper called the Fast Downward Planning System, which is a general purpose planner, but it's actually turned into a kind of melting pot now of all sorts of different planning techniques. So originally an implementation of the Fast Downward Planning System, now this general framework for solving planning problems. It supports Astar Search that we've been talking about so far. There are multiple ways you can search graphs as well, so we've also got support for eager breadth-first search, greedy search, enforced hill climbing, iterated search, and some other things. But interestingly, it supports many different general-purpose heuristics. So goal counting is one. If you can subdivide a problem into a set of smaller problems, and as you solve those problems, that counts as decreasing the heuristic. Fast forward and fast downward are kind of the algorithms that were invented around the time of the Fast Downward project. So fast forward came first, fast downward improved on that. And I'm not really going to focus on how those heuristics work, although the paper is a very nice paper if you find you're interested in this work. HMAX and HCM, kind of more historic heuristics that were at the start of this type of research. Landmarks is an interesting one where you can kind of identify key points in the search graph that you're always going to have to go through. So I like to think of a logistics problem of moving parcels around the world. If you have to move from one country to another, your landmarks might be the airports between the two countries. So the landmark heuristic is capable of working out these landmarks for any graph, which is pretty impressive. And we've got two modes of input here. There's PDDL, which I think is the problem domain definition language, which is a Lisp-like language. It's very high level and it's standardized. And the goal here is to have a language that you can pass between different solvers, because Fast Downward is not the only solver of its kind. And it's very much intended for humans to write. But that's not too much of interest to me, because I don't want to write these things by hand. I want to generate these things from Haskell. But the good news is there's also this bespoke graph format, which is definitely intended for machines. It's an entirely nameless representation, so the file is just entirely integers and entirely unreadable. But it's perfect for targeting from a domain-specific language. So that's the setting the scene, I suppose, of what planning problems are. I'm now going to move on to the Haskell side of things. If anyone has any questions, I'm happy to take some now on this idea of planning problems. Okay, well, feel free to grab me. Oh, we do have one, yeah. Hang on, we've got that mic coming.
So you mentioned earlier that these problems can often involve rather large graphs.
Mm-hmm.
So it's always the case that you must define the entire graph at once, or can you sort of lazily, as the thing explores, begin to provide more and more view into the parts that it's...
So what we're doing in Fast Downward, we do essentially build the entire graph. I would like to see, now that we've got a kind of, as we'll see here, the Fast Downward Haskell project is kind of a domain-specific language for solving these problems. I'd like to see if we can do an in-Haskell version that kind of benefits from just lazily expanding the graph.
Yeah.
Right now, yeah, it can often be for very, very large graphs, you spend more time building the graph and then trivially search it, which is unfortunate, but yeah.
Cool.
All right, so Fast Downward, the Haskell library. It's a very, very concise API. It's modeled on the STM API for software transactional memory. Turns out those are very similar concepts in STM apply to the Fast Downward library. And there are three main concepts in the library. So we have mutable variables, which are used to encode the state that changes over time. We have effects, which model all the possible actions that can occur. And then finally, we can solve problems by given a list of all possible effects that can happen and a list of tests, which are essentially kind of equality checks between variables. We can solve a problem to return a sublist of effects that we should apply in order to reach our goal. So this is the API for variables. We have an opaque data type var, which wraps up any Haskell type A. We can construct new variables. So given an initial state that we know to be true for that variable right now, we can construct a var A inside the problem monad. Problem monad is not particularly interesting. It's really just there to set up the initial state of the world. And then we have two operations on variables. We can read from them and we can write from them. So given a var A, we can get back the A's inside a variable. And it's interesting to note that read var is actually a non-deterministic read. So you won't read a single assignment to this variable, but you'll actually read all assignments that happen over the course of a planning problem. Write var is kind of more deterministic, I suppose. You write a single value into that variable, and that will cause other read vars to kind of continue their evaluation and observe a new value at a new point in time. The API for effects, so effects are just monads, so we have instances of functor, applicative, and monad, so do notation and things like that just fall out very naturally for writing these effects. Because we're working in this idea of a kind of non-deterministic computation, we've got monad plus alternative and monad fail. Monad fail is especially useful as it gives us pattern matching inside do notation. So if we were encoding a problem, for example, where we have some kind of robot gripper that can pick things up, the gripper can only pick something up if it's not already holding something. So I might read the state of this kind of gripper variable. If it is holding something, I'll just abort the transaction entirely. So again, we've got read var and write var live in this effect monad, so that's the only place where you can read and write to variables. And then finally, we've got one function to solve problems. So solve takes a search engine, which is how you're going to explore the search space. Fastdownward being very configurable, we've got all the configuration options just packaged up into that type. It takes a list of effects, which are those atomic effects that can transition from one state to another. A test, which is essentially a quality checks on variables taking particular values at the end of the solution. And we're going to get back a solve result, which is really just a kind of list of steps that you would have to take in order to move from the initial state to the goal state. And just down here at the bottom, the kind of top level running function that takes you out of the problem monad and puts you back in the IO monad. So to see how fastdownward can be used, I just wanted to run through a couple of slightly contrived but not entirely unrealistic examples of automating a smart home. And we'll see most of the concepts of the fastdownward API will be used as we go through these problems. So the first problem that I want to solve is I have a single light, and that light can be turned on. The light is initially off, and I need to use a very sophisticated planning engine to work out how to turn the light on. Maybe a little unrealistic, but we'll see most of the concepts of the API here. So the first thing I'm going to do is just kind of introduce this call to run problem, which allows us to work inside the problem monad, and ultimately we're interested in getting some kind of result from this. First thing I need to do is set up the state of the world, so I'm going to construct a new variable which tracks the state of that light. So a light can be turned on and a light can be turned off, so bool is a pretty good type to track the state of a light. So the light variable, if it's true, that corresponds to the light being on, but the light is initially off. And then I just make my call to solve. So I need to specify some kind of search strategy. So I'm going to use Astar Search, little overkill, but whatever. My single effect that I could possibly do is to turn a light on. So I'm just going to write true into the light variable. And this is the test that I'm interested in being true at the end. So the light variable should contain the value true. Leaving the problem monad, we can then just pattern match on this result variable. So that's a solve result. One of the constructors, which we would hopefully get, is solved, which gives us back a solution. And from a solution, I can extract a totally ordered plan, which is just a linear sequence of steps that I should apply. Sorry? We will see that shortly. So now I can just go into GHCI, I can type hello, and I see my plan, which is list unit. So that's a little concerning. That doesn't seem particularly useful. The idea of a plan is it's something you could give to an execution engine, but I can't really tell somebody to go in unit. That doesn't really make any sense. So why is the plan the singleton list containing unit? So if we recall, the type of solve took a search engine and a list of effects of type A and a list of tests, and it gave us a problem, a solve result in the problem monad of that same type variable A. So in our case, we have solve Astar Search, write var light true. That write var light true has type effect unit. So list write var light true has type list effect unit. So therefore, when we called solve, we got a solve result that contained unit. So really, the conclusion here is that your individual effects that you provide should return some kind of metadata on how they should be executed later. That is kind of the hint is right there. We should return metadata, so we can just use return to augment that write var light true action by just returning some arbitrary metadata. It's up to us exactly what we choose. It doesn't get provided to the solver at all. It's just purely a Haskell value, so we can use whatever we want. So I'm just going to use a string. And now when I run hello, I get the single action plan, switch on the light. Very useful. So problem 2 is a little bit of a richer problem. Now I have multiple lights. These lights can be named, and lights can still be turned on or off. And I want to write a command line application that actually turns a subset of lights on. So I'm not just interested in a plan, I actually want to do something with this plan. So fast downward being a Haskell library, I have all the normal kind of Haskell means of abstraction available to me. The first thing I'm going to do is build a little domain-specific language for myself to model these lights. So what is a light? A light I'm going to represent as a record containing the name of the light and a variable that tracks whether or not that light is currently on or off. I need a way to construct these lights. So if you give me the name of a light, I can give you back a light value. I just use a bit of applicative syntax here, pairing up the name with the light constructor and initializing the isOn variable to false. So lights begin out as false. And then I had to consider the effects that a light can produce. So we can either switch on a light or we can switch off a light. And I'm going to encode that a bit more structurally now with a proper type for the metadata of what a light does. So switch on takes a string, which is the name of the light to switch on. Switch off takes the name of the light to switch off. And for a given light, there are these two possible effects, which we produce as a list. So I can write to the isOn variable the value true, which indicates that the light state is now on. And I return the structured metadata saying switch on that light. Likewise, I can switch off a light by writing false into the variable, and I'm just going to return switch off light. So then, recall that the problem we're trying to solve here is build a kind of command line application where, given a list of lights, I can turn them on. So I'm going to write a function that takes a list of light names and produces an IO action. So the first thing I'm going to do is call run problem to enter this kind of fast downward API. And then I can just use normal Haskell functions to build up my state of the world. So I'll just map m new light over the list of all lights that I know about. And then again, I make a call to solve. So solve needs to have access to this list of effects that could happen. And the list of effects is for every light, I have a set of light effects. So I can just concat map light effects over all lights. And I then have access to all light effects over all of those lights. And then for my test, I need to specify these kind of equality checks. So I'm going to use a list comprehension here. I'm going to go over all the lights that I know about. If that given light's name is in the goal, so the lights that I want to turn on, I'm just going to check that its isOn variable has the assignment true. Again, I can just pattern match on the result, witness the solution, extract a totally ordered plan. And here's like an example call. I might want to turn on just my office and kitchen light, and that tells me indeed to switch on just the kitchen and the office light. It didn't tell me to switch on the bedroom light. It could have, because there's actually a solution there of switching on all the lights, but that would be a longer plan, so we're actually prioritizing the kind of shortest plan that will get us to our goal. But this, of course, is not the finished solution. So we were interested in actually executing this plan as a command line application, but the moment we've got one of these plans, we're just back in the IO monad, and we can do whatever IO we want to do with the plan that we've just achieved. So here I'm going to use the Heu API, which is a library that's on Hackage. So I just need to use run Heu with the host for my controller for my smart lights and some kind of API key. Then I can just use for to loop over all elements of that plan, pattern matching on each of the metadata constructors. So if the plan tells me to switch on a light, I will just make a call to the Heu API's update light function and actually turn that light on. So that's how you can take one of these kind of plans that are in this kind of abstract state and actually realize it and execute that plan in the real world. So problem 3, I thought this was a very contrived problem, but actually after interfacing with that coffee machine outside, I feel maybe it's not entirely made up. So we've got a strange coffee machine here that is capable of doing some individual tasks. It can measure and grind some coffee beans, it can boil some water, it can brew a cup of coffee. It can do any of these things at any point in time. So it has no internal state itself. If you press the brew cup of coffee button and you haven't boiled the water, you will just get a cold cup of coffee. But of course, it's Internet of Things, so I can do all of this over an API. And my problem here is I want to use the fast downward API to finish off this coffee machine and actually have it easily produce cups of coffee. So I need to come up with a plan in order to make the perfect cup of coffee. So again, I'm going to model my state here by introducing a new record, which represents what a coffee machine is. The coffee machine is actually 3 independent variables. We have a Boolean variable that tracks whether or not the water is boiled. We have this free state coffee beans variable, which tracks the state of the coffee beans, so they can either be unmeasured, they can be measured, or they can be ground. And then we have this brewed variable, which is really a kind of output from the system that I can observe turning into true when a cup of coffee has been brewed. So I can create a new coffee machine. I initialize the water boiled variable to false, so the water isn't boiled. The beans haven't been measured, and I don't have a cup of coffee yet. So now I have to consider the actions or the effects that can apply to this coffee machine. So boil water is one thing we could do. The effect here is to, first of all, I'm going to check the current state of the water boiled variable just to be a bit more energy efficient. If the water is already boiled, then we'll abort the transaction. If the water is not already boiled, then I'll carry on to the next line here, which will set the water boiled variable to true. So we update the internal state that we know about. I'm going to return this boiled water metadata constructor telling me that I need to make that API call. This is not strictly necessary. You probably wouldn't end up with a plan repeatedly telling you to boil water, because that wouldn't be the shortest possible plan you can come up with. But it can be quite nice sometimes to just kind of encode a nicer specification in these effects. So we have a slightly more interesting effect here for working with the coffee beans. So if there's 2 things I can do to the coffee beans inside the machine. I can either measure them or I can grind them, and it requires me to do those in a particular order. So to do this, I'm going to have one effect that just manages the state of the beans. And here we see that idea of a non-deterministic read. So the first thing I'm going to do is read the current state of the coffee beans in the coffee machine. Sorry. I'm going to have a look at what that returns. So if the beans are currently unmeasured, then I know that what I can do is I can measure those beans. That then, by writing measured into the coffee beans variable, will cause this read var to have a new possible path out of it. So now I will be able to read measured from the state of the coffee beans variable, in which case I can write ground into the coffee bean state. I can return this metadata that instructs me that I'll need to make a API call to grind the beans. And again, read var will have a new possible state that it could read, so it could also read ground now. But if you've got ground beans, there's nothing more to do, so we just simply return empty and terminate the transaction. The final effect that we've got is to finally brew a cup of coffee. That's going to bring in all of these variables together and see how they interact. So I can only brew a cup of coffee if I haven't already brewed a cup of coffee. If I try to brew a cup of coffee with a coffee in there, it'll just go everywhere, and that's going to be a mess. The next thing I'm interested in is making sure that the water is boiled. I need to make sure that the coffee beans variable currently contains ground. So here we see that we get nice syntax using monad fail. I can just pattern match on variables exactly. And if all of these preconditions hold, then I can set the brewed variable to true and return the API call to brew a cup of coffee. And the last thing we need to do is just kind of bring all of those things together into a list. So now the coffee machine problem, again, I use run problem. I build a new coffee machine, initializing the state of the world. When I call solve, I have access to all of the things a coffee machine can do, but I'm only interested in a single variable taking a particular assignment, which is that the brewed variable is now true. Again, I can print out the totally ordered plan for this, and it tells me to boil water, measure the beans, grind the beans, brew the coffee, which is exactly what I want, but I would question that if this is actually the best cup of coffee that I could make. And the reason I say this is because we have to understand that this list here corresponds to a list of actions you have to take in order, and you have to take these actions to completion before you begin the next one. So this would mean if I actually tried to do this, I'd boil the water, and I would wait until the kettle was actually boiled before I began measuring beans and grinding beans. So obviously now, if I take my time measuring the beans and grinding the beans, the water's going to cool down, and I don't have the best cup of coffee possible. So what I'm interested in really is some notion of concurrency. I should be able to boil that kettle and measure and grind the beans in parallel, and it's only once both of those things are done then I need to join together and actually brew a cup of coffee. The fast downward API supports this as well. We've seen so far that we've only been extracting totally ordered plans. You can actually ask for a partially ordered plan, which will attempt to recover some notion of concurrency. So I didn't have to add any type of concurrency primitives to my problem at all. I just observe a slightly different solution from the solution that the planner gave me. This is not always guaranteed to be the optimal concurrent solution, but I've found most of the time it does a good enough job. So now we can see we've got 2 things we could do in parallel. We can measure the beans, boil the water. Once the beans have been measured, regardless of the state of the water, we go ahead and grind the beans, and once both of these 2 nodes are both complete, then we can join together and brew some coffee. Last thing I wanted to do is just kind of bring all of this together and show you how we can use Haskell's normal means of composition to compose kind of multiple problems together to solve richer problems. So now I've got my smart house, which has 3 lights. I've got one of these strange coffee machines, and I want to come up with a morning routine plan. So my morning routine is that the bedroom light is turned on, a cup of coffee is brewed, and once that cup of coffee is brewed, the office light is turned on, because I never go into the office without a cup of coffee. Seems reasonable. So to model the state, I'm going to introduce the same kind of pattern before. So we have a new data type which represents what a house is. So my house consists of these 3 lights. That's the light type from the kind of light API we saw before. And one of these coffee machines from the aforementioned coffee machine library. And to build up the initial state of my house, I'm just going to construct the 3 lights, bedroom, office, and kitchen. Construct a new initialized coffee machine and just return that as a house value. I then have to consider all possible effects in the house. And you might naively think we can just concat all of these effects together. That's generally the right idea, but if we do that, we're going to get a type error. And that's because the metadata for all effects has to coincide. We have to have the same type of metadata. So light effects return light metadata, the coffee machine returned coffee metadata, so these types don't unify. That's a very easy problem to solve in Haskell. We just introduce a new type to kind of unify these types together. So these are all house effects, and a house effect could either be interacting with a light or it could be interacting with a coffee machine, and we can just use this kind of combination of fmaps to munge all of this data together into a single list. So now I can have a look at this idea of a morning routine. So I construct a new house. I'm going to solve with access to all effects in the house, which is all of the ways the light can change and all the ways the coffee machine can change. And I'm interested in this statement at the end. The bedroom light should be turned on, the office light should be turned on, and the coffee machine should have brewed a cup of coffee. And this visualize solution thing is just going to visualize one of these concurrent graphs of how to execute this. And this is almost correct. So it's telling us that right from the start, we can switch on the office light, switch on the bedroom light, and then begin using the coffee machine. That's not quite what I was interested in, because this is slightly inefficient. I don't want to turn the office light on before the coffee is brewed. I want to pause this action until this one is complete. But we can augment existing effects just using normal monadic combinators. So the code comes out a little bit scary here, mostly because I was trying to squeeze it into one slide. But the idea is if we go over all the effects that an office light can produce, so this is a list. This operator here is just a kind of map operator. So I'm going to map over all the effects that an office light could produce. This gives me access to an individual office light effect. I can go ahead and run this, and then I can actually observe what metadata it produced. So the office light effect could produce switch on. And if it is trying to switch on the office light, that could only happen if the coffee machine has brewed a cup of coffee. So I can augment this action with a little bit more information. So if this guard fails, then the office light will simply not be turned on. If this guard succeeds, then we'll just proceed to the end of the block and we'll return the instruction to switch the office light on. So this is the only change I need to make. All of the rest of the code remains exactly the same. And now we get this slightly different graph that tells me once I've managed to brew a cup of coffee, I can then go ahead and switch on the office light. So that's the idea of the fast downward API. Obviously, this is quite a small little example that we've been working through. So here are some examples of where you could use this kind of in a bit more anger. So of course, CircuitHub used this to coordinate all the actions in the factory. We introduced data types for the individual machines in the factory and all the state that we care about on those machines, such as what program is loaded into a machine, what circuit board is in that machine, whether or not it's running a task, and things like that. But we can also integrate this whole fast downward library into a kind of richer application. So we've got a servant-backed web server with an in-memory job queue that we can submit jobs to, and it will automatically begin executing those. Our execution platform is a kind of hybrid platform of both interacting with machines in the factory and just doing things automatically. Or if we don't know how to do something automatically, we kind of schedule that out to one of the engineers in the factory and have them execute that just individual tasks. So we're kind of augmenting the capabilities of the engineers in the factory and automating a lot of the kind of redundant work. And then we reflect all of that planner state just back into a normal Postgres database so we can resume planning at any point in time. Another option, I think you could use fast downward as a kind of package manager. So a user might specify the goal state that Nginx is installed. And in terms of planning, we might work out that we need OpenSSL to be installed along the way. Maybe it's not the best application of fast downward. Sat solvers and things probably do a better job, but I think you could do that. I think you could do something a little bit like Terraform. That was originally what I was planning to talk about, but it turns out it's a little bit harder than just about 45 minutes of work. But I think you could do it. And the idea there is you want to be able to say predicates such as, I have a database server running, and that would get realized into a plan that knows how to spin up AWS nodes and things like that and load the correct AMI onto the machine. You could also build, I think, a database migration library, and this is actually what the Beam Migrate library does on Hackage. So the idea here is your database is a deterministic system. The actions of a database are to add tables and to add columns, to delete tables, and so on. So if you encode all the possible ways you could mutate a database, you can actually come up with migration strategies. You're interested in reaching a state where certain tables exist and certain columns exist and things like that. So that's also doable. But that's, of course, not exhaustive. If you're interested in reading a little bit more about this project, this is the Fast Downward homepage where you can read more about the solver itself. This is the library that's available on Hackage. And I've also got a blog post running through a kind of another running example of using the Fast Downward solver to solve a problem of moving a couple of balls from one machine to another using a robot, which is kind of like a canonical example of these type of solvers. And I just wanted to see how it could be translated into Haskell. So I think that's everything I really want to talk about for this. I'd love to take some questions. We got the cube? Yeah.
Do you have a notion of time? So if you're trying to manage your factory and you want lots of things to happen at once, you want your circuits to come out at a time, then do you need to model each variable at each point, what the state of the machine is at each point in time?
Yeah, so this planner is specifically interested in non-time-based plans. So you're not interested in how long it takes to execute things. That's why we have that ability to recover some type of concurrency, because that, in the context of the factory, we're more interested in being able to do things in parallel rather than knowing exactly how long something's going to happen. Most tasks take about 2 to 3 minutes to execute, so even if you can recover some concurrency, that's pretty good. I guess you choose.
So the effect monad is about specifying edges.
Mm-hmm.
What is the format of edges in the generated program? Because it looks difficult to me to generate code because it's monadic.
Yeah.
So how do you do that?
So the code that's generated to the solver is essentially just lists of edges. And the way that actual monad works uses continuation passing. So every time you do a read, we capture the remaining continuation. And whenever you write, I kind of re-invoke that read and produce the new reads that come out of it. So I don't think you should really be concerned too much about the code that's generated, because it's almost like an entirely internal...
My research is about code generation.
Oh.
So I tend to be concerned with these matters. Okay.
Sure.
So in the first example where you turn on one light, you were using Astar for the solver, but you didn't specify any heuristics. So how did that work?
So let me see if I've got this open. Yeah. So yeah, let's have a look at what actually happens when you call solve. That's one bit I did skim over a little bit. We give it a search engine. Oh, nice! I got no internet. I believe I would have been using just some of the kind of general purpose heuristics there, or maybe even just a blind heuristic of just do a kind of brute force search. Landmark heuristics is what we use in the factory. So that just recovers kind of key points that we're always going to have to go through. So that's the heuristic that I think we're using in the factory. Let me see if I get that turned on. And I'll see if I can bring that up in a bit, but yeah.
Do you want to go first?
I still don't fully understand. So you specify these actions, and presumably you analyze these actions to produce your graph.
Mm-hmm.
But those actions, they can execute, they're running Haskell code, right? So if you, maybe I read the value of my light, and I do A if it's on, and B if it's off.
Mm-hmm.
So now how do I produce a graph from this?
What's actually happening is, so with this call to solve here, we give it the list of all known effects. The first thing I'm going to do as this Haskell library is kind of exhaustively search all the effects you gave me to build the entire search graph. And the reason I can do this is because the effect monad only really has 2 operations, to read from variables and to write from variables. So the idea is I notice every time you read from a variable, because I implement that code, and by using continuations, I get to suspend that read and keep track of the fact that you're interested in this variable. And then I go ahead and just run all the other effects, and if any of them write to that variable, I can then kind of re-invoke that continuation and begin producing more information.
Gotcha. So you figure out exactly the full set of values that this variable could possibly have.
Yeah, loosely speaking, I'm a little bit more intelligent than that, and I try and work out, like, if there are writes that I just deem uninteresting, I kind of prune those out early. So I try and build a minimal graph for the problem you're trying to solve. Yeah.
So you provocatively said that we could use this for a package solver, right? But I won't delve into that one. But there must be a similar example with your factory, right? Because you don't want a factory says no answer. So how do you deal with error messages or error reporting? How do you find out why the solver says no?
The current API we have there is somebody sends me a message on Slack. So this is something that I'm not happy with. It's got the same problem with sat solvers and stuff. If it does just say this is unsolvable, so you can see here solve result is either unsolvable, it crashed, or here's your solution. I don't know right now how to get better information out of that as to why something is unsolvable.
Okay, so we won't replace the Cabal solver just yet.
That's your choice.
Thank you.
Me. I guess, what happens if the graph is infinite?
This will not terminate, yeah. So usually the problems as you tend to encode them do come out quite naturally finite, so you'll work with kind of fixed enumerations of possible values. But if you do introduce something like a natural number that could increase, you have to be very careful that you guard that. So actually I do have an example. I thought it would be fun just right at the end to come back to that agent that we were looking at. See if that comes up. We'll do it here. So this is how you can solve that agent problem as well, but we encoded the state there as a pair of integers. So you have to be very, very careful with this guard right at the bottom that says that your new x and y coordinate are within the current bounds that you know about. If you don't, this will just build a very, very large search space. But coming back to Ben's point of being able to kind of build this thing lazily, I think if you could do that, you could deal with infinite search spaces, possibly with a timeout or something. But yeah, maybe of interest to people, this is how you would solve the agent problem as well. So the agent can move forward, backwards, left or right. We're going to encode it with just a single variable, which is a pair of integers, which is the location of the agent. The possible effects, I just enumerate all of the possible movements. I read the current location, check the direction I'm trying to move, and just update the state accordingly. And if you plug that in to solve again, you come up with a slightly different path, but it is equally short, of just moving right twice and then moving forward 3 times. But yes, to your point, you have to be very, very careful that this line exists.
So I guess a corollary of that is that all the variables need to have eq instances on the values, so they can actually check whether 2 states are the same?
I mean, for the problem encoding, yes. For the API, it doesn't actually matter. So I currently need ORD, but that's just there because I build a map of assignments. Yeah, I think you do need EQ actually, yes. Otherwise you'll just re-exhaust things you've already seen.
How fast is the one iteration of planning?
So we are solving problems at Circus Factory. It takes about 10 seconds to generate the graph, and then solves in about 7 seconds, which for us, that's real time enough for our purposes.
So you you can't use this package in game engine?
Probably, I mean, it really depends on the size of the graph that you search. So CircuitHub has this, like, the graph ends up having this unique property that there's all sorts of kind of unrelated bits of state. So every circuit board obviously has its state, and if you place a circuit board in one location, that produces a huge graph based on all the other circuit boards. And then if you move that circuit board, that produces another massive graph. So you get this kind of combinatorial explosion. If whatever game you're working with doesn't kind of have that property and the graph remains quite small, then you'll get very fast results. So the example mentioned here of this like fast downward blog post of moving a couple of things from a room to another, that terminates in about 0.01 seconds. So it can be very, very fast, but obviously that's a very, very small graph to search.
So this library executes some executable to produce results. Is there any way to, I think, short circuit it with FFI or something?
Possibly. I mean, it's a C++ library, so we might be able to extract like a kind of core out there and just do a native call. The execution model at the moment is to basically just spawn this process, pipe the plan in standard input, and it gives you a plan in standard output. There's a little bit of overhead of marshalling there, but I'm not sure FFI would be too much quicker. You kind of still need to build the graph and hand the graph over somehow.
This thing's padded, eh? So you mentioned, you have this whole sort of discussion was about, well, I want to build one circuit board, but you don't want to build one circuit board. You want to build many, and orders may come in as you're sort of in the midst of already carrying out a plan. So are you intelligent at all in sort of trying to update your existing sort of ongoing plan, or do you just start, if you have a new order that comes in, you just drop the old one and construct a new graph, and then with the current state of the world and just resolve?
Yeah. So the model of how we're using this at the moment is more as a kind of interactive tool. So it's here to help engineers in the factory kind of do the rest of their work. We don't have full automation over everything yet. The factory we've got has been around for coming up to 2 years now, so it's still pretty young. So the kind of problem that we're trying to solve immediately is allowing an engineer to just kind of schedule a piece of work and then focus on another piece of work. So we have people managing the factory saying which orders we're going to produce on any given day, and you essentially use the solver to do what are still, I mean, I still consider them slightly too low level. So you'll say things like, I need this circuit board in this machine. So you're not really interested in how that happens, and it'll solve the constraints along the way, but I'd like to be able to say in the future, okay, this circuit board needs to be finished. And like kind of start to do things like that. I've got some internal models that kind of prove that it works and comes up with plans. It's more, do I trust all of the execution along the way to not just suddenly output a circuit board and be like, it's finished, and there's just solder paste all over it. And so I do hope we'll get there, though. That's the long-term goal with this.
Cool. Very nice talk. Thank you.
Yeah, I think Adam's got one.
Yeah. So a sort of follow-up question to this. I mean, can you deal with the real world being non-deterministic and the possibility that you don't know what state you'll end up in if you carry out a particular action?
There are non-deterministic planners and probabilistic planners and things like that that really deal with that in their notion of planning. In this, you could still kind of do that, though. I think you essentially need to watch how the real world is changing as you're doing your execution. And the moment, you essentially need the ability to reflect the real world state back into your model. So if you kind of do that in parallel as you execute something, if you ever diverge, you just need to stop what you're doing immediately and replan from the current point in time back to that goal. That's essentially what we do at CircuitHub. So people can interact with the factory as it's executing something. So if somebody moves another circuit board around, that will stop what it's doing and it'll replan. And usually it just carries on doing what it was doing anyway because that change is unrelated. That would probably be how I'd kind of approach that problem. So essentially watch the real world, and the moment you diverge from what you thought was going to happen, you need to stop and replan, if that makes sense.
So one quick, more technical question. So you do all this stuff by generating the graph, the whole graph, and then you pass it to the C++ program. Is that the?
Yeah.
So if you wanted to do the, lazily generating the graph and then doing the breadth-first search or Astar or whatever, you'd have to do that and then both in the same. I mean, you then can't use the external C++ solver because it needs the entire graph up front.
Yeah.
So maybe you could perhaps do the lazy and then infinite search spaces if you can Yeah, but then you have to do it all in one. You'd have
Yeah,
to do it
I
all
mean,
in the Haskell side.
this is a established C++ project with it actually seems to be coded fairly intelligently. So I do think you could probably extract like a library out of that and maybe get access to some kind of incremental solving step.
Okay.
So if I can essentially plug into the state expansion function, then I may be able to lazily generate the graph.
Right, but it would need to be able to deal with a graph that it hasn't seen all the edges yet.
Which is going to be very difficult for some of the heuristics like landmarks, which require you to statically analyze the whole graph at once.
Yeah. Okay. Yeah.
Okay. So, thanks again, Ollie.
Thank you.
Yeah.